Okay, so let's talk about another application of the derivative. And this is an application that allows us to find the zeros of functions in certain situations. So let me just remind you a little bit about what we said when we discussed the intermediate value theorem. So suppose that I have a function that's continuous, and so I'm actually going to pick a very specific function, x squared minus 2. And now what I want to notice is that f of 1 is equal to negative 1, and f of 2 is equal to 2. Now, negative 1 is going to be less than 0, and 2 is going to be greater than 0. So what that means is if we look at this closed interval from 1 to 2, now because f is continuous, it's a polynomial, it's a continuous function, what can we conclude? Well, we can conclude that because f of 1 is negative and f of 2 is positive, there must be, so by the intermediate value theorem, there must be a number, and we're going to call this number x star, between 1 and 2, such that f of x star is equal to 0. Okay, so now of course, you can sit here and say, well, yeah, I know there's a number between 1 and 2 for which f of that number is 0. I can just pick the square root of 2. And so, of course, x star equals the square root of 2. But I claim that saying x star is equal to the square root of 2 is no more enlightening than just saying x star is a number between 1 and 2. As of right now, all I know about the square root of 2, which I'm calling x star in this case, is that it lies in the open interval between 1 and 2. So the question now is not a question of whether or not f has a 0 or 2 has a square root between 1 and 2, because of course it does. The question is, how do we actually figure out what it is in terms of a decimal approximation? So for instance, is it less than 1.5? Is it bigger than 1.4? Is it bigger than 1.4111111? How can we say more precisely what x star is? What is this number, so to speak? And that's exactly what we're going to do right here. We're going to figure out a way to use the derivative of f to actually figure out with pretty good accuracy what the square root of 2 is. Now, if you recall, we've already talked about one idea, and that's the linearization of f of x. So the linearization and now remember, when we do a linearization, we actually have to pick a point to do the linearization at. And so let's actually do it just at x equals 1. So at x equals 1 is given by what? Well, it's f prime of 1 times x minus 1 plus f of 1. Okay, so f prime is 2x. We plug in 1, we get 2. Okay. So f prime of x is 2. We plug in 1. And we'll get 2. And then we have x minus 1. And then minus 1, because plus f of 1, so that's minus 1. Okay, and this is basically what the linearization is. Now, remember, the linearization is not the function, but it's basically the line that's the closest to the function. It really is the tangent line at this particular point, x equals 1. So what we can do is, instead of finding the 0 of f of x, we can actually find the 0 of this function L of x, the linearization. So we'll find the 0 of L of x. But that's really easy to do, right? So, I mean, you can just set this equal to 0 and solve. But what you're going to see is that we're going to get x is equal to 1.5. And now what we're going to do is we're going to call this x sub 1. Okay? Because this is the first step in this algorithm called Newton's method. So it's just doing a very simple thing. We have a function. We're trying to find the 0. We're calling that 0, that function x star, which in this case we know to be the square root of 2. So what we do is, the first step is just to linearize f of x, find the linearization, and then find the 0, and we get that x1 is equal to 1.5. So what we can say is that x star is approximately 1.5. That's sort of a first step approximation. Now, of course, this is still off by a good bit. If you plug square root of 2 into your calculator, you're going to get something like 1.41 and then some more decimals. But you see that at least doing this first step, we're getting something that's pretty close to the square root of 2. It's getting pretty close to the actual 0 of this function by just looking at the 0 of the linearization of the function. Okay, so just to say again, our goal is, given a function f of x, find a 0 of f of x. Okay, so we said that if we linearize the function at a point and find a 0, that will be an approximation of one of the zeros of f of x. So just sort of to show you a picture, if I have a function like this, let's actually give it a 0. So here's our function, f of x. And if I linearize the function, say here, so I find the linearization of this function, so the tangent line, then I can pretty easily figure out the 0 of this linearization. But of course, what I'm going for is the 0 of the function that we're calling x star. So you see that the 0 of the tangent line will be an approximation to the 0 of the function. And now the closer we take the linearization to the actual 0, we're hoping that the closer this approximation is going to get. Okay, so like I said, finding this x1 is going to actually give us the first step in what's called Newton's method. So here's what Newton's method is. And again, the goal is to find a 0 of f of x. So step 1. Pick a starting point. So I'm just going to pick some number. And now you say, okay, well, how in the world do I know which number to pick? Well, it doesn't really matter, but it does matter if I have some idea of where the 0 of the function is. I probably want to pick it near where I think x star is. The closer I pick x0 to x star, even if I don't know exactly where x star is, maybe I just have a small interval where I think x star is, I want to pick x0 as close to that as I can, because that's going to increase the likelihood, first of all, that Newton's method is actually going to give me a good approximation to x star, and second of all, it's going to ensure that I'm going to the right 0, because if you think about it, f might have more than one 0. So if I pick an x0 close to 1, 0, it might approximate that 0. But if there's another 0 I'm interested, I probably want to pick a value closer to that 0 that I'm interested in. Okay, so step 2 is I'm going to linearize, so give the linearization of f of x at x0. Okay, and then I'm going to let x1, so let's say the linearization is L, let's say 1 of x, say L0 of x, and we'll let x1 be the 0 of L0 of x. Okay, so I linearize f of x at x0, and now I'm going to call that L0 of x because I'm linearizing at this point x0. And then I'm just going to let x1 be the 0 of L0 of x. So in our picture right here, here's x1. And then what I'm going to do is I'm going to linearize f of x at x1. Because theoretically, or I guess I hope theoretically, x1 is going to be closer to x star than x0. So after doing this linearization, I really am hoping that x1 is closer to x star than x0. So then if I linearize f of x at x1, and let's call that L sub 1 of x, the next step is going to be to let x2 be the 0 of that linearization. And then I'll just say etc. Because you can repeat this process as many times as you want. And under certain conditions that maybe are a little technical for this class, beyond the scope of this class, but under certain conditions, these kind of sequence of points, x0, x1, x2, x3, I'm getting by doing this process over and over again, should be getting closer and closer and closer to x star, the 0 of f of x. Okay, so repeated application of Newton's method is going to give me a sequence of points or of numbers. So Newton's method gives a sequence of points. Okay, and so if this word sequence is new to you, it really doesn't mean anything. It just means exactly what I'm about to say. So remember, x0 was my initial guess. x1 was the result of taking the linearization of the function into x0 and then finding the 0. Then x2 is the result of taking the linearization of the function in x1, finding the 0, and then so on. I can repeat this process as many times as I want, okay? And as I said, under certain conditions about the function, so certainly the function needs to be differentiable. You know, the other thing to think about is I'm going to be extremely unlucky if I pick an initial point that has a horizontal tangent, because then there's not going to be a 0. But I mean, all of those things are very technical, and I just want to give you an overview. So under certain conditions, so skipping some technicalities, the limit as n goes to infinity, so if I just keep doing this process over and over and over again, these x of n's that I'm getting are going to converge to x star. And now, what do I mean by converge? So, in other words, xn, the sequence converges to x star. And what I mean by converge is exactly this. The limit of these points or these numbers in this sequence are getting closer and closer to x star as it goes to infinity, as I do more and more and more steps. But you see that, you know, in reality, I don't want xn to be literally equal to x star. You know, in most applications, I really probably just want xn, my approximation, to be accurate up to 5, 6, 7, maybe in really crazy cases, 10 decimal points. And the cool thing about Newton's method is that we are going to get that level of accuracy typically after just 2 or 3 iterations. So x2 and x3 typically are extremely close to x star. And so remember, the whole point of all of this is that f of x star is 0. Okay, so I'm trying to solve this equation for this x star, and maybe x3, f of x3, is very, very small. So x3 is very, very close to x star. Now this does not always happen, but this is the goal. The goal here is, you know, after just a few steps, for f of x3 to be very, very small, meaning that x3 is very, very close to x star. And again, this will happen under certain conditions, and the conditions are pretty reasonable. So let's actually go back to the example we were talking about and see how this process, Newton's method, works with our example of the square root of 2. Okay, so remember that we had the function x squared minus 2. And we knew that the square root of 2, which, let me just use a calculator. And so it's probably worth noting that methods like this, approximation algorithms like this, are actually how a calculator computes these values. So if you ever wonder, well, how does my calculator know what the square root of 2 is? Well, it does in an approximation algorithm similar to Newton's method. And so using a calculator, we see that the square root of 2 is 1.41213526237. So here's something, just to think about. If we're accurate, so if we get an approximation that's accurate up to this many decimal places, that is as accurate as we will ever need to be for pretty much any application. I mean, you're talking about if you're making a measurement, and let's say even if this is meters, even if this is like 1.4, etc. meters, the most precise instruments that we have are only going to be able to measure accurately up to 5, 6, maybe 7, 8, 9, 10, you're getting at that atomic level where there's just really no point in getting more accurate than that, because there are going to be other problems that come up. Okay, so I know I'm just going off, but let's just see how Newton's method works. So we already did the first step. So we started with x0 equaling 1. And we found that x1 was 1.5. Okay, so you're already saying that start just picking something close to square root of 2. We just know that square root of 2 is between 1 and 2 by the intermediate value theorem. So we just picked 1. We're already getting pretty close, okay, after one step. So now remember, to get x2, the second approximation, we need to linearize the function at 1.5. Okay, so I'm just going to tell you what that is. So I think this is what we called L1 of x. And then you just do it, okay? It's just f prime of 1.5 times x minus 1.5 times plus f of 1.5. Maybe I'll just write that down. So f prime of 1.5 times x minus 1.5 plus f of 1.5. I mean, all of this is super easy to do. And then we find the 0. And what do we get? Well, we get the next order approximation is 17 over 12. Okay, so 17 over 12. That is 1.41 and then 6, just repeating 6's after that. Okay? But that's looking pretty good. We're already accurate up to 2 decimal places, 1.41, 1.41. So I'm not going to write down all of the steps, and I'll say that something with Newton's method. Newton's method is typically implemented on a computer. Okay, so using your favorite programming language, Python or MATLAB is actually a really good choice for Newton's method. Just running that program, you can very quickly, you don't have to do all of this by hand, is what I'm saying. And so I'm just going to, I wrote a program that does this, and I'll just show you the outputs, but what it's doing every single time, so to get x3, you just linearize the function at 17 over 12, and then find the 0, and what you get is 577 over 408, which is 1.4142158. And then some more stuff. So now we are really cooking, right? So 1.4142. Now we have 4 decimal places we're accurate up to. Actually 5, it looks like, even. This 5 and 3 are the first time we differ. And look at what happens if we just do one more step. So the 4th step in Newton's method gives, okay, so we linearize the function at x3, find the 0 of that linearization, we get 6, 6, 5, 8, 5, 7 over 4, 7, 0, 8, 3, 2. And here's where it gets really amazing. This rational number, fraction, is 1.41412627 and then 4. Repeated. So you see that just after 4 steps of doing this very simple process of taking a point, linearizing the function there, finding the 0, taking that point, linearizing the function there, taking the 0, doing that 4 times, we have pretty much the most accurate approximation to the square root of 2 that you will ever need. And so this hopefully gives you an appreciation for how calculators work. Now, calculators typically don't use exactly this method. They use a little bit more sophisticated methods. But you can see how quickly a computer could do this. I mean, a computer can do, these 4 steps of Newton's method to approximate the square root of 2 in fractions of a second. And then you get it. And that's amazing. You can get exactly, not exactly, but, exact enough of what the number, the square root of 2 is. So it's pretty cool. It's a very powerful method. And so the last thing I want to do is actually show you a picture of what's going on here. Okay, so here's a really cool picture to look at. So this function in blue is x squared minus 2. And we know that the graph of x squared minus 2 crosses the x-axis, somewhere between 1 and 2. So 1 is right here. This is actually equal to, I think I did this actually with x0 equaling 1.5 to start with. So I actually used the first order term first. So you start here and then you draw the tangent line. Okay, and you see that the 0 of this green line, this first green line, gives us x1, and then we go up to the function, and then we linearize the function at that point, find the tangent line, find the 0, that gives us x2, find this tangent line, that gives us x3, and look how close. I mean, I don't know if you can zoom in, but you see that here's x3 right here at the top of that cursor, and then the 0 is right there. They're very close. And you see, if you did this again, I mean, on this graph, there aren't enough pixels here to even differentiate if we did this again. So x4 is going to be right on top, right on that pixel where actually the 0 of the function is. But this is just a visualization of what's happening. You pick a point, tangent line, find the 0. that point, find the tangent line, 0. Take that point, find the tangent line, 0. And you just keep doing this, and you can kind of see this convergence process. You're just getting closer and closer and closer to the 0. And actually, like I said, under certain conditions, we can say something very formally that the limit of these points, or these numbers in the sequence, actually converge to, or the limit is equal to, the 0 of f of x. Okay, so here's example 1, and now I've actually already done all of the work here because I really am not going to write out anything by hand. Like I said, Newton's method is an approximation algorithm. It's a technique in the study of numerical analysis. It really belongs in and of itself, kind of purely in a programming setup. So, you can do Newton's method by hand, and it's not a bad idea to kind of understand. And that's what we did with the example x squared minus 2. But really, it's really straightforward. And if you have any programming experience, I encourage you to try this, but to write a program that actually implements Newton's method. Because then you can just plug in whatever function you want, and you can just start finding zeros of functions pretty easily if you write a program. So here I just have the output. But now the equation we're starting with, so if you recall back on the lecture on the intermediate value theorem, we actually showed that the equation x squared is equal to 2x has two obvious solutions, x equals 2 and x equals 4. And then one not so obvious solution that we call x star, and it's between -1 and 0. So we know that this third kind of not so obvious solution to this equation must lie in this interval -1 to 0. Again, that's by the intermediate value theorem. And then you can just take my word that the function satisfies these mild conditions that we need for convergence, so we can apply Newton's method. And here's the table of the first few iterations. Okay, so we started with x0 is equal to -0.5. So this was my guess right here. So the first, the x sub 0 really is just a guess. I just picked the midpoint of the interval that I knew the 0 had to lie in by the intermediate value theorem. And now here, what I'm plotting over here is actually f of, in this case, -0.5. Because remember that f of x star is 0. So if f of xn, it's getting closer and closer to 0, I know that xn is actually getting closer and closer to x star. Okay? So then what the computer does is it linearizes the function here, finds the 0. There's the 0. Linearize the function here. Take the 0. Linearize the function here. Take the 0. Linearize the function here. Take the 0. And there's 4 steps. And now if we use a calculator, here's what the calculator actually outputs. So this will be accurate up to all of these decimal places. And we see that the first decimal place where they're different is the 11th. 1, 2, 3, 4, 5, 6, 7, 8, 9. Well, okay, I guess this is the 10th decimal point. But it is correct up to that 10th decimal point where we're getting a 0 where we should have gotten a 6. But like I said, that is very accurate. That is very good. And if this was a measurement, then we would be well within the tolerance of any measuring device that I know of. So it's pretty cool. Okay, so again, just using the same program that I wrote that just takes a function. So in this case, we're trying to solve this equation cosine x is equal to x, so we're going to let f of x be cosine of x minus x, because a 0 of that function will be a solution of this equation. And when we talked about the intermediate value theorem, we actually showed that this equation has one solution between 0 and pi over 3. And so now pi over 3 is a little bit bigger than 1, so I just chose x0 to be equal to 1. And we see that f of 1, so cosine of 1 minus 1, is actually already pretty small. Well, 0.45, negative 0.45. So then we linearize. That's what the program does. It linearizes the function here and then finds the 0. Then it linearizes the function here, finds the 0. Linearizes the function here, finds the 0. And after 3 steps, if we compare what we get to what we get in the calculator, we see that it's very close. It's correct up to 9 decimal places, which is awesome. So that's the idea of Newton's method. Again, I think that if you're interested in this sort of thing, it's a little bit outside of the scope of what's covered in calculus. The main purpose of introducing it in calculus is because it is, one, just an extremely important application of the derivative. I mean, really, it's just an application of the linearization of a function at a point. But it's really cool that you can use that simple idea of linearization to actually find zeros and approximate zeros very accurately. But if you're interested, there are courses in numerical analysis that you can take. You can also probably find a lot of good resources just on the internet. And it's not a bad skill to have, to be able to program something like this, because in reality, when you're solving equations, a lot of times the answers are not very nice. You have to approximate. You really don't have a choice. So being familiar with these approximation algorithms are just very marketable skills. So I encourage you to look into it, but that's just an overview of what Newton's method is, what the purpose of it is, and then a couple of examples of how you can approximate zeros of functions.